Hello everyone. So now we are going to talk about joint probability distributions and probability generated functions. Um, so in this lecture, we are really going to focus on joint probability distributions um, for discrete random variables. So x and y, if we take two random variables, they both are going to be discrete random variables, and we want to talk about joint distribution of those two random variables. Before we continue, in my last lecture, I wanted to show you probability distribution with infinite expectation. So here's example. So let's say you define random variable with probability x equal x taking n is non-negative, n is positive integer, is 1 over n time n plus 1. Okay. Now, once you define this, you can calculate the expected value, which is going to be sum x time probably x take a little x, so to our example is n time probability x equal n, which is going to be n time 1 over n time n plus 1. Now this one is going to be this one is going to be the sum of 1 over n plus 1. And start from 1 to infinity. Now, you can show that this series is divergent, which is standard exercise in calculus 1. So since this one is divergent, the expected value is infinity or not finite. By the way, remember that we have a rule saying total probability need to be 1. So if you add this probability, it should be 1. So check that whether it's right or not. The easier way you can expand this, it's going to be 1 over n minus 1 over n plus 1. Then see when you sum up that, it's going to be 1 over 9. It's an infinite series because n goes from 1 to infinity. You can still show that it's going to be 1. Okay, so let's go back to our original discussion, joint probability distributions. So you can have two random variables, x and y, from the same probability experiment. Then you can define the joint distribution of x and y using this formula. So here x taking x and y taking y. So instead of this long expression, you can write it as simple way like this. But when you say this, you need to remember what that means. For example, we just write probability x. What that really means is probability random variable x taking that little x value. Okay. The same way, probability xy mean probability random variable taking x and random variable y taking little y value. Okay. So if x and y are independent, of course, we know that probability a and b, if a and b are independent, then we can write as product using multiplicative rule. So you can simplify it and write it as this. So here actually this is, I would have to be careful, this is from random variable x probability, that distribution. And then this is actually random variable y. This is joint distribution function. This is not, I should have included x and y here. So if x and y are two random variables with distribution functions, probability of x and px and py, then we can calculate expected value of x plus y first. So how do you calculate expected value of x plus y? If I use a definition, this is going to be what? xy, I mean, it would be x plus y time probability xy. This is a joint distribution function. So here, let's say x can, let's put xi, yj, okay, that we can add index here, so it's ij. Okay. So this one you can see, if I expand, this is I across I and across j. So I have xi plus yj. Okay. So this one you can show, you can break it. You can break it, you can multiply xi time pxi yi and then yj time pxi yj. And then you can show that it's going to be ex plus ey. Okay. So that's something I didn't include here. Okay. But that's how you prove that particular result. Then you can prove that the second one, this one, exy equal ex times ey. By the way, when you are proving here for this one, just remember that if you sum across, let's say j, okay, then that's going to be what? That's going to be probability xi, because you are adding across all yj. Okay, so this would end up as probability of xi. That's something you need, because once you expand this, you would need that. In the same way, if you sum across I, then this would end up as y yj. Okay, so use that and then try to prove the result. Okay. All you have to do is expand and then see if you can get it. The same way you can prove the next one, x value of xy is going to be x value of x times x value of y. Okay. To prove this one, start from here. You can see this is going to be what? You can write xi yj times pxi yj. But since they are independent, remember we are assuming now independent, this is going to be probability xxi, probability y yj. Okay. So once you have that, then you can kind of like break it. And then you can prove that this is, I mean, you can prove this result. Similarly, try see whether you can prove this one. It should not be that hard. This is only true if x and y are independent. Okay. Otherwise, you will have covariance terms in the middle. So just try to prove the result using x, y independent. And then also see what is the formula if x and y are not independent. Just be curious and see what happens if x and y are not independent. What would be the variance formula for x plus y? This slide, you will see a function called probability generative function. So let's say x taking a random variable, taking non-negative integer values. So what that means? X can take 0, 1, 2, so forth. And then we define probability of x equal n as Pn. Okay. Then the probability generative function, or you will see like PGF, for x is defined using this formula. So S is basically x by value of Sx. If you expand this what? Sigma S. I can, let me write this way, x equal some I, then the probability x equals some I, and then I goes from 0 to infinity. Remember, x take only non-negative integer values. So because of that, basically you can say you don't have to write like this way. You can just write as I, or even this one you don't have to write that way. You can just write pi. Now, if you take the, so let's expand this and see what that is. This, if you expand it, this is what? S0, P0, S1, P1, S2, P2, so forth. Okay, what is P1? That's the probability, random variable taking 1. What is P2? Probability, random variable taking 2. Okay. So if you differentiate this respect to S, H prime S, what's going to happen? You would have, this one is 1. Okay, by the way, this is 1. So you would have P1 plus 2 times SP2 plus 3 times, I mean, if I write the next one, 3S square, P3, and so forth. Okay. Now, if I set S to 1, it's going to be what? It's going to be P1 plus 2 times P2, 3 times P3, so forth. So which is going to be a sum of, you can say, I can just put 1 here. This look like what? This look like x time probability x equal x. In this case, 1 times P1, 2 times P2, so forth. So this is x-ray value of x. So that's first result. Okay. You may wonder why we are really why we really want to learn about this. Another reason for probability generated function, I mean, why we are introducing it, because if you know probability generated function, then you can get the probabilities very easily. All you have to do, you have to just differentiate and get the answer. So so let's go back to this expression. Okay. So what is H0? H0 is P0. Okay. What is H prime 0? H prime 0 is P1. What is H double prime 0? Okay. If you take the second derivative and if you differentiate this, that's going to be actually 2 times P0, or 2 times P2. And then if you take the H triple, the third derivative, and take that, it's going to be 3 factorial and P3. So in general, you have a formula, which I didn't write here. Probability x equal n, or Pn, is basically 1 over n factorial time h prime, I mean h n 0. Okay. So this one is very useful, because if you know the probability generated function, then you can get the probabilities, and then you can get the expected value, and then you can also prove the variance is going to be like this one. So knowing probability generated function is very useful to get all these other quantities. Okay. So here you will see a little bit more application of probability generated function. We define k factorial moment using this formula. And then you can see that the first factorial moment, second k factorial moment, the expected value of that you can get by taking the k derivative of probability generated function and evaluating at s equal 1. Okay, so that's all for this lecture.